Okay, so continuing on with our idea of the transmembrane potential, and we were talking about sodium moving into a cell and bringing a positive charge with it, and we were talking about potassium leaving the cell and leaving a negative charge behind. So let's put this together into what it's actually used for. So why this is important at all and why we're talking about it for so long. So we'll start over here. When we have something called a depolarizing graded potential, that is when we bring a positive ion into the cell, like we saw with sodium. So we open a sodium channel and we bring sodium in, and sodium diffuses across the cell membrane. That is a depolarizing graded potential, or you could call it a depolarizing local potential. And the reason why it would be called a local potential is because it just conducts. So it's conducted across the cell membrane. So this is a relatively slow, electrically speaking. So when you're talking about electricity, it's kind of always rather quick. And that's what this is. It's an electrical charge, but it's a relatively slowish one that's going to be diffusing in all directions around the cell membrane. And that would be called a depolarizing graded potential or a depolarizing local potential. You can also call this an EPSP, and that word stands for excitatory postsynaptic potential. And the reason for that is that when you depolarize the cell, it's tending to get you closer to that threshold that we were talking about for our voltage-gated channels, which are found on the axons. And when you reach that threshold, you open them and you have an action potential, which is how all of this works. It's how when you do any sort of neuron being stimulated and releasing neurotransmitters because of an action potential. So this would be tending to bring you closer to having an action potential, maybe even stimulating an action potential. Not necessarily, it has to be strong enough, but that's the idea behind it. That's the whole purpose of it. So the way that we get these, the way we can make them stronger is by opening more channels. So let's say we just have a leak channel open. There's really not that many leak channels on the cell membrane, so that's not going to do a whole lot of good. It's not going to do anything to depolarize you to the point of having an action potential. But if we open some gated channels, let's say some chemically gated channels, so we open a bunch more, now we can have more sodium channels coming in. There's stronger or more depolarizing graded potentials, or EPSPs. They're all diffusing around. They're added together. So we have a much, much stronger EPSP, much stronger stimulus. Now, if we keep opening these channels, so let's say we open them once, this is going to dissipate. It's not going to be quite as strong as we keep opening it, and we just keep having sodium coming in, more sodium, more sodium, and we get a stronger and stronger charge. This whole process that I just went through is called summation, where we add up our EPSPs in this case. We can also do it in the other direction, but let's just stay with EPSPs right now. Where we can have it happening over an area. So we open 1, 2, 3, 4 channels instead of just one. So that would be called spatial summation, because we're opening channels over a space. Or we can have it temporal summation, where we have over time. So same channel, open, over and over again like that. So that is how we get a stronger depolarizing graded potential, or stronger EPSP. Now for the opposite situation, hyperpolarizing graded potentials, or IPSPs, which would be inhibitory postsynaptic potentials, because they're tending to get you farther away from having an action potential. They're tending to inhibit the cell. And they're called hyperpolarizing because they're making you more polarized, more negative inside. So we could do that by opening potassium channels. So out goes the potassium, leaves a negative charge in its path. If we open more, now we're getting into summation again. We're leaving more of a negative charge. More potassium leaves, and more of a negative charge. If we keep them open, so we open, 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 then more negative charges as the potassium leaves. So we can sum up the IPSP in that way. Now we can put these together by adding them both up. So if we have, say, a neuron, there's our neuron, and we want to see if it's going to have an action potential or not. Let's have a couple of neurons all converging on it, because that's really more like how it's going to be working. It's not just going to be one neuron communicating with just one other. It'll be a whole bunch of neurons, hundreds, even thousands, communicating with one. So let's say this neuron is telling the neuron that we're talking about to have this situation. It's telling it to open sodium channels and have a depolarizing graded potential. So we get that happening there. And let's say this one is opening potassium channels. So we end up with a hyperpolarizing graded potential, or an IPSP. And then let's have this one do another EPSP, so telling it to open sodium channels and depolarize. So we can add up the total of the charges to see if we get to the threshold here at the initial segment of the axon. Now threshold is negative 60 millivolts typically. That's not working. Threshold, negative 60 millivolts. Okay, so if we started out at negative 70, we need to have a change of to negative 60, so a change of positive 10, right? Because the difference between negative 70 and negative 60 is plus 10. And that plus 10 charge has to reach that initial segment of the axon where we find the voltage-gated channels, which will open if we get them to negative 60 millivolts. So let's say our EPSPs were 15 millivolts, so positive 15, and our IPSPs were, say, negative 4 millivolts. So in order to determine if we're going to have an action potential, does this come up to a change of positive 10? Do we end up at negative 60 instead of negative 70? So you do the math. You do negative 70, that's where you started. You add 15, so that is, negative 55. Doing it backwards. And then we have negative 4 that we have to add in here. So we do minus 4, and that puts us to negative 59 millivolts. That is more positive than negative 60. So we open the channels, we've hit threshold, we can have an action potential. Now if these IPSPs were, say, negative 10, so we would do negative 70 plus 15 is negative 55, and then we'd have to subtract 10, so that would give us negative 65 millivolts. That is not more positive than negative 60. It's more negative than negative 60. We didn't hit threshold. We don't have an action potential. Nothing happens. So those IPSPs can completely negate anything that the EPSP is trying to do. Now, another way that we can have an IPSP is not by a hyperpolarizing graded potential, but by something called a repolarizing graded potential, which, if we remember our chlorine channels, we can do if we are already having a depolarizing graded potential. So we know that chlorine, if we're just at resting, chlorine's not going to move across the cell membrane if we open a channel. But if we have this positive situation here, and we open a chlorine channel, chlorine will move in just enough till it, negates each positive. And it depends on how many you open there. So this is another form of an IPSP because it's inhibiting the stimulus of the positive graded potential here, this depolarizing graded potential. It's canceling it out. For every chlorine you bring in, you cancel out a sodium, which is trying to stimulate the cell. But you're not going to get it more than negative 70. You're not going to get it any more negative than that. So you can't hyperpolarize here, but you can have a repolarizing graded potential. Okay. So all of these things will be coming into play on any given neuron. Some things are going to be opening sodium